Jezebel, there are certain tasks that in this class of yours, you are a great group to work with. I do have to say that. I'm glad I'm saying it before the semester ends and before I forget. So you are a great group of people to work with because you have unofficially appointed people. So Jezebel always remembers the lecture number. If I ask a question, Russell is the spokesperson of the class, and thank you, sir, because he will respond. And then Amir and Karan, they love that chat. They will do epics, and the other ones will just do epics. But you are a great group of people to work with. So if this had to happen, I'm glad it's you. So let's do this. Okay, so no questions there? Oh, it's the truth. I love those. I love you. I love that group of people. You're a very sane group of people. Maybe I'm facing insanity somewhere else, so it makes you just look good. But you are good. Okay, so Trent, I've no idea what you're saying. So I'm out of a job. That I understood. What do you mean I can't read a textbook anymore?
Because we're not in class.
Oh, he's talking about that. Okay. God, yeah. It is too early in the morning, isn't it? Oh, there you go, Trent. Yes. And I miss that. So, and I miss how, now I have to go back and read the problems, and you're so right. And then I have to decide the problems beforehand. That's too much work. I just like coming in and saying, people, here it is, pick a problem and we'll do it. So this is just too much work. It takes too much planning beforehand. Okay, so let's start before further ado. And here we go. So reminding you, recall, that we started with the concept of sequence. For those of you who have taken discrete math, you will see, or for those of you in computer science, you are going to look at sequence in a different way. So I'm just going to throw it out there. But sequence is a list of terms. In some ways, I'm going to say it's a collection of elements. So what collection? Oh, it is A1, A2, A3, A4. So this is the first term of the sequence. This is the second term of the sequence. The third term, and so AN would be the nth term of the sequence. So how do we represent this sequence? So we represent this sequence by AN, which is the nth term. This parenthesis is the set notation, which denotes the collection. So the idea is that if you find a formula for AN, the nth term, then by putting n equals 1, n equals 2, n equals 3, you should be able to generate the entire sequence. Entire list. So what is one way to look at the sequence? So you can think sequence is a function from the set of integers to the list. So where F1 is A1, F2 is A2, this is how discrete math will look at it. F3 is A3, and so on and so forth. That is the same thing as saying, oh, the first element is A1, the second term is A2, the third term is A3, and so on and so forth. So you can think of a mapping as a function. So it maps 1 to the first term, 2 to the second term, 3 to the third term, and so on and so forth. So the story goes now. So what were you interested in? This is an infinite list. At this point, I really want everybody to stop because I'm going to give one of my weird analogies. But remember, the analogies are for you to take or leave it. So if it doesn't make sense to you, just throw it off. If it does make sense, then latch onto it. So everybody ready? Nobody writing? So I want everybody just listen to me and see if it makes sense. So when I look at this sequence, I'm looking at a comet with a very large tail. So you are observing this heavenly body, this comet, and the tail doesn't seem to end. But somehow you have got sort of a mapping for it in the sense that you're saying, okay, this is the first position I saw. Then this is the second position where I can trace the comet, the third, the fourth, the fifth, and so on and so forth. And I can trace the bits of this comet. And it seems to extend so long. So you just want to say that eventually what happens to this comet? Is there an end to this, or the tail just goes on and on and on? And when I say on and on and on, remember in space, when we observe objects, the heavenly objects, it's not that they don't end or they are all of them are infinite. It's just we can't see them. So I'm just going to talk about that. So in other words, you want to know that I can't see the tail of that. But I want to know does it end or does it just continue on and on? Which means I want to know that this list that you gave me, does it converges? So does a sequence converge? Or diverge? And for that, I'm going to look in the infinity, which is limit as n approaches infinity of an, meaning I want to know the behavior of the terms. As I look into eternity, which means however far I can look. So as n approaches infinity. And then we said, if this is a finite number, then the sequence converges. You know CGS is converges now. If this was an infinite number, which is plus or minus infinity, I shouldn't say infinite number, that's spooky. So if it's infinite, or the limit does not exist, which means what? It oscillates. It doesn't come to one place. It just goes up and down. So then we say that the sequence diverges. So I just want you to keep that in mind, that if I want to know a sequence converges or diverges, then you know you have to come up with this an. Then you have to take the limit. And then you have to go on from there. So any questions? And was the analogy too weird? Did it make some sort of sense?
Made a bit of sense.
Okay, fair enough. So if it was in the classroom, then I would have waved my hands about, I would have gotten an idea of looking at your faces, if that makes sense, or that's complete nonsense if I have ever heard one. But so can we go with Russell? Some sense then? That's the verdict out there, people? So type in something. So some sense is, so you're saying yes for some sense. Good. So it's not, so I'm going to take this as half glass full, which just means to me it was not complete nonsense. Okay, thank you, Sam. So here we go. So now we are talking about series. So what are series? And I'm just going to say, what is a series rather? So the story goes, you have a sequence, which means you have this list. And I'm asking what I'm asking because another batternology coming up. A3, A4, A5. Now what do you choose to do? You choose to make another sequence. And how do you make another sequence? Or you're saying S1 is A1, S2 is A1 plus A2, S3 is A1 plus A2 plus A3. So where am I going with this? Oh, I'm making another sequence, Sn. Well, what is Sn? Sn is sum of first n terms of the sequence. let's look at how series is written in notation. So I'm just going to write it in notation. So here it goes. So S4 is going to be the sum of first 4 terms of the sequence. So of course, it's going to be A1 plus A2 plus A3 plus A4. You've got the idea. Sn is going to be A1 plus A2 all the way up to An. And here's where we introduce the notation. So series this is summation. This is the Greek letter sigma. It's an uppercase letter. So this denotes summation. From I equals 1 to infinity AI, which means, and this I is an integer. So I goes from 1, 2, 3, 4, all the way up to infinity. So in some ways I like to say this is the start and this is the end. Start or end to what? The number of terms that you're adding there. So this is going to be A1 plus A2 plus A3 plus A4 all the way up to infinity. So my question to you, how many terms are we adding? So how many terms are we adding? Both Amir and Cecily look at the start and the stop. So is there a stop?
Is it infinitely many terms?
Correct. And I'm going to write that. So Amir and Cecily said something. So for them, I'm going to write this. So what about this one? So again, this is the start. This is the end. And what is this I? This I is an integer, meaning you're going to tell yourself I equals 1, 2, 3, 4, all the way up to n. So we have A1 plus A2 plus A3 all the way up to An. So this is Sn then, isn't it? Because the sum of first n terms. So I'm going to give you a couple more. Now tell me what is this one. So I want everybody to say it or type it. Number 1. And so this will be so I'm asking about number 1, and so this will be, you can say it, you don't have to type it. So Cecily, how far do you want me to go? Here? There we go, Trent. Very good, Joshua. So Cecily, you're going to let me know when you want, we are ready to proceed. So I'm ready to pause. And okay, no worries. So any questions there? Because you're making this series. So I'm just going to say, I'm just going to write this. This was the correct answer. A1 plus A2 plus A3 plus A4, A6 plus A7. So I'm going to say in this notation, oh, this is S7 then. So going back there, a series is represented by, given by, represented by, I'm just trying to grab the pen, and I'm just going to write how your book writes it, An, which is A1 plus A2 plus An somewhere, plus all of this. Now I'm going to the book notation. They're saying let Sn denotes its partial terms. Actually, I don't like that. So I'm gonna make my own thing. So here we go. So from this one, we can say that S1 is A1, S2 is A1 plus A2, S3 is A1 plus A2 plus A3. In other words, I have created a sequence S1, S2, S3, S4, somewhere is Sn, and so on and so forth. So I'm just going to write what it means. This is the sum of first two terms. And this is the sum of first n terms. And I'm going to give you an example right away. But the only question I have for you is, if I want to know whether this sequence converges or diverges. Converge or diverge. Then what am I supposed to do? And I'm going to go back to what I know about sequences. So tell me, what am I supposed to do? If this is the sequence, S1, S2, S3, I don't care how it is formed. You're just saying S1 is just A1, S2 is A1 plus A2. For me, they are still numbers because you're adding the terms. So S3 is A1 plus A2 plus A3. I like what you're saying, Sam, but take the limit of what? So if I want to know if this converges or diverges, then I have to take the limit, you're absolutely right, n approaches infinity of what?
The series?
So this is the sequence. This is what I'm talking about, right? That S1 is A1, S2 is A1 plus A2. That's going to be some number. S3 is A1 plus A2 plus A3. So if this is a sequence, then isn't this the nth term of the sequence? Because this is the first term, the second term, the third term, the fourth term. So this is the nth term of the sequence, yeah?
Mm-hmm.
So I'm supposed to take limit as n approaches infinity of Sn. How do I know that? Because that's what you said. You said if there is a sequence, which is just a list. So this is just a list. It's just that I'm making that list a little bit differently. That's all. So if this is just a list, then take the limit of the nth term. So here is an example. And this is how I'm going to kind of explain. And this series will come together. So here's example one. And I want you to look at it and answer me. So here is the sequence. So the series in this case is I equal 1 to n ai. Sorry, I'm just going to, the series in this case is I equals 1 to infinity ai. What the heck is ai? I'm going to write, this is your A1, A2, A3, A4. So can you tell me, can you write out this series for me? So what is this series then?
Isn't it geometric?
Well, I'm not even asking you that. I'm just asking you very, very simply, what is this series then? If this is A1, A2, A3, A4, A5, can you tell me what will AI be? Let me go to the notation used by the book. Because I is just a dummy variable, so I could change it n equals 1. Okay, so if A5 is 1, the fifth term is 1, can you tell me in this sequence what will be the nth term? An? Look at the list, Amir. Very good. So it's going to be 1. And so when I say n equals 1 to infinity an, what does that mean? Oh, I'm going to add 1 plus 1 plus 1 plus 1 all the way up to infinity. That is what it means. So what about that S1 then? And I'm going to say, oh, S1 is just 1. S2 is 1 plus 1, sum of first two terms, which is 2. S3 is 1 plus 1 plus 1, which is sum of first three terms, which is just 3. S4 is, of course, 4, and so on and so forth. So I'm saying that this series that you see on the top is really a sequence of what? A sequence of partial sums. So if I want to know this series converges, then I'm going to look at limit n approaches infinity of Sn. So for all of you, here is the question. What is Sn in this case?
It'd be 1, wouldn't it?
Remember, Sn is the sum of first n terms. So question to you is, you're adding n number of terms. What are your terms then? What do the terms look like?
The terms look like 1 at least.
There we
The
go.
terms are an.
Here we go. So I am going to erase that and I'm going to start writing in the notation and you will see what I mean. So Sn is summation I equals 1 to n of 1. What does that even mean? Oh, you are adding 1 plus 1 plus 1 plus 1. How many times again? N times? So tell me, 1 plus 1 plus 1 plus 1 n times is what?
Whatever the n value is.
Okay, this is Friday. I forgot. So I want everybody to stop writing and answer this question for me. So if I add 2 plus 2 plus 2 3 times, what is the answer there?
6.
So can I say the answer is 2 times 3? If I add 2 plus 2 plus 2 plus 2 5 times, what is the answer there?
2 times 5.
Very
so
good.
10.
So I want to say this to you that, and this is the basics of mathematics, and I'm just recalling it. See, every time in mathematics, you have to understand why we do the things the way we do them. What do I mean by that? Oh, repeated addition is multiplication. Because if I want to add 2 plus 2 plus 2 plus 2 20 times, then you don't want me to write this 2 plus 2 and you're just sitting me watch there, writing this 20 times. You're going to say, wait, we got it. So it is 2 times 20 then, isn't it? And now let's go take a bit further. So what about repeated multiplication? Oh, repeated multiplication is exponent. Because if I'm going to multiply 2 times 2 times 2 times 2 times 2 20 times, I don't want to write that. So I'm just going to say this is 2 to the 20. So repeated addition is multiplication. Repeated multiplication are your exponents. And that is the shorthand sort of that we do in math. So coming back here, now we are saying if it is 1 plus 1 plus 1 n times, then the answer Sn is going to be, and look at these two.
1 times n.
There you go, sir. So I'm trying to erase all of this. So here it is. And I'm going to make my point, so stay with me. It's going to come all together, but you need to see a couple of more examples. Series is a very conceptual thing, and you have to grasp to the concept because there is no algebra here. So Sn then is going to be n. So my question to you is, does this converge or diverge? And for that, you're going to say, okay, limit as n approaches infinity of Sn is limit as n approaches infinity of n. And what do you think? It converges or diverges? So the limit will be what?
Infinity.
There you go, infinity. So this definitely diverges. So I'm going to go to the definition in your book. So here it goes. And here's how I'm going to try it all together, which is given a series. And this is in your book. Summation n goes from 1 to infinity. When they give you that one, I want you to understand, oh, this is a1 plus a2 plus a3. So can I say this is an infinite sum? And notice what you are asking yourself. And this is where you have to understand what are you asking yourself? The question you're asking is the same that you were asking before. Does this converge or diverge? Now pause a little bit, stop writing completely and start thinking for me. How many terms are you adding again? So when you saw this series, how many terms are you adding again? Infinitely many terms. When you are asking it converges, what was your definition of converge? That the limiting value should be finite. So what are you asking? You are asking, does this infinite sum, or I should say, is infinite sum finite? And that is so counterintuitive. That is what you're asking. So when you're asking if it converges, you're saying, is this infinite sum finite? And today I'm going to show you, yes, there are some infinite sums which are finite and which you've seen actually, which you know. Infinite terms add up to infinity. That doesn't surprise me because I'm adding infinitely many terms. So again, how many terms am I adding? I'm continuously adding. And then if I'm adding like that, and then the terms get bigger, the infinite sum goes to infinity, that doesn't bother me. But this is very counterintuitive to me. So because I'm asking, is the infinite sum finite? If the answer to this one is yes, we say it converges. Then we want to know, what does it add up to? So it adds up to what? And today, as we go further, I'm going to show you what it adds up to. So you're going to find everything. You're going to find this. But does the series converge or diverge? So going back there, your book says, given this series, this is me talking in between because we want to find if it converges or diverges. The question is, how do you do it? Oh, you are going to find Sn. What is Sn? Sn is the sum of its first n terms. So Sn, I'm writing in many or different ways, is A1 plus A2 plus A3. Sn is also summation I goes from 1 to n. Yeah, now he uses I, Ai. So your first job is to find Sn. Number 2, take the limit as n approaches infinity of Sn. And if this is convergent, if this limit is little s, what is this little s? It's a finite number. Then you say two things. You say the series converges. Not only that, you're saying the series adds up to, that infinite sum adds up to s. In other words, you're saying summation n equals 1 to infinity an is s. So you're telling me what the infinite sum adds up to. If this is divergent, which means this is infinity or does not exist, then we say that the series is divergent. Remember convergent, divergent, and whatever the third one was. I'm talking about the books now. Insurgent? Probably. There you go, Karan. So insurgent. So I want to kind of go back to the last example. So what was the last example? Oh, the series was summation I equals 1 to infinity, or n equals 1 to infinity 1, which was what? 1 plus 1 plus 1, blah, 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 infinity. What did we do? Oh, we found Sn, which you said was 1 plus 1 plus 1 n number of times, which was n. We took the limit and we said this one just diverges. So far, so good. So here is the next series for you. Here's my next example. And you're going to tell me if I need to pause. So ready for the next example? And I promise you, it's all going to make sense, but I'm going to work off of this one now. So you are given a series that looks like that. And you are going to find Sn and so on and so forth. So here's my example 2. Ready for this one?
Yep.
Okay, so here we go. So the series I'm giving you is this one. Now think about before you answer this. So when you're doing this for me on the test, number 1, and this is me teaching to the test, write out the series first. Which means write out the first few terms. So tell me, this series is what? N equals 1 to infinity, n will be what? And I want you to recall, this means you're just adding them. This is the start. And each one of them is an integer. So I'm just going to say to you that when n equals 1, it will be 1. N equals 2, it is 2. N equals 3, it is 3. I'm supposed to add them. So this is what this series looks like. Agreed.
Yep.
More importantly, any questions there? Because you have to absorb the notation here. Thank you, Russell. So this is the series. So what do you want to know? You want to know, is this infinite sum finite? That's the question. If it adds up to something, if it converges to something, we are interested. If it diverges, we are not interested. So what is going to be the first part of this class? Just separating the convergent series from the divergent series. So you just want to recognize, looking at the series, running some test on it, whether it is convergent or divergent. Giving a bad analogy again, which is in the times we live right now. I just want to know if you are infected or you're not infected. It's convergent or divergent. If you're not infected, go home. If you're infected, then isolate, take care of yourself, and so on and so forth. That is what we are talking about. So that is what we want to do with this infinite sum. But look again, what you're asking yourself. I don't know, I teach this so many times, and this just blows my mind. How would you even think of an infinite sum adding up to a finite number? Because it's very, very counterintuitive. So going on from this one, what was the thing there? You are telling me, oh, find Sn. So what is Sn? It's the sum of first n terms, which means it will be 1 plus 2 plus 3 plus 4. Where should I stop? So this is the first term. This is the second term. This is the third term. What would the nth term be? And I want an answer from you. And I'm just going to write this in notation. Oh, this is going to be I equals 1 to n I.
Isn't this the 1 minus an?
Russell, you're going way ahead for me. I just want Sn is 1 plus 2 plus 3 plus 4. Where should I stop? If A1 is the first term, A2 is the second term, we do understand we are adding A1 plus A2 plus A3 all the way up to An. So my question is, what is the nth term here? If A3 is 3, A4 is 4, A5 is 5, what
n.
is? There you go. So I want to, this is Sn. So what do we want to know? The question is, do you know what this adds up to? Because once I know what this adds up to, I can take the limit. The answer is yes. Discrete math tells us that the sum of first n integers is n plus 1 over 2. So now I can take limit n approaches infinity, n plus 1 over 2. Care to tell me what the limit would be?
0.
Russell, in your mind, you have inverted everything. So I'm just going to say, as n approaches infinity, what happens to these two?
They get larger and larger.
There you go. So the limit is going to be what? Infinity? Right?
Yeah.
And so this series diverges. And now what is the problem? The problem is it's not easy to find this Sn. So not at all easy. You cannot find it for all kinds of series. So it's not easy to find Sn. So actually we're going to find Sn for a particularly important series. So I want to pause here. I want everybody's complete attention because that is how I think of series. So think of series. So this is going to sound very cruel, right? Yeah, but at the same time, we have grocery stores opened. So, and this is a joke for all of you boys. One day you're going to get a list, which is going to be a grocery list. 10 years from now, 20 years from now, I don't care. Just because you're not built for grocery shopping, you're going to mess it up. But that's besides the point. So you are going to get a very detailed list. Just because you're not used to this grocery business, no matter how the list is going to be, you are going to mess it up. So I want you to imagine. Ignore all the comments now. I want you to just listen to me. So here is your grocery list, which is A1, the first item, A2, second item, A3, third item, fourth item, fifth item, and whatever. So imagine this is infinitely long list. So you are going to go around the grocery store with your cart, and as you grab an item and you put it in, say cereal, for example, that's going to be A1, A2, A3. So next time you go grocery shopping, you're going to think to yourself, oh, this is the sequence, because this is a list. A1, A2, A3, A4, A5, and so on and so forth. I don't know if Vincent is here today, but Vincent should get this because he works there. Then you come to the cashier. And what does the cashier do? She scans your A1 plus A2 plus A3 plus A4. That's a series. So for me, that is what is sequence and series is. So you have a list, which means you gathering things in your cart. Once you get to the counter, then you have A1 plus A2 plus A3. Karan, don't get cheeky with me. A3 plus A4 and A5, and that's going to be a series. So the closest I think you can get with what I'm saying is, do you know that show Extreme Couponing something? Does anybody know this? Have you watched it?
Sorry, watched what?
Extreme Coupons. I don't know what it's called. There you go. Bumnit is going to pass this class. So they're full of cards. So Russell, just kind of educating you on that one. It seems this is what Karan prompted me to go there. So this was because of Karan's cheekiness. So they collect coupons. Russell, they shop for 6 hours or something in a store, and they have these carts full of things, and that is A1, A2, A3. That's the closest I have seen a human come to infinity. So they just shop and shop and shop those items. No, Karan, this was good because they shop and shop and shop those items. So as I said, that's the closest I've seen them come to infinity. So they have 6 or 7 carts full of stuff, Russell. And then they go to the counter, and then the counter itself takes what? Some kind of time to scan them. So it is A1 plus A2 plus A3. That's the series.
Got you.
Does that sit well with you? But as I said, that's the closest I have seen in a physical world a human come to infinity. Because I don't have the patience for spending 6 hours on anything. Yeah, there you go. So Aaron, these kids, my God, Russell, they're so ahead of their time. They're watching grocery shopping. I can't believe you kids. This generation is something else. I was not thinking of grocery shopping when I was 18. God knows what I was thinking, um, but these kids, see, look at the charts, Russell. They're watching grocery shopping.
I mean, when I was their
Like,
age, my grandma was making me watch The Price is Right.
but the Price is Right is even exciting. Go and watch that show for me over the weekend. It's
Alright.
like, yeah, they just shop, and these kids are watching them. Oh God. Okay, but if that's helped you understand sequences and series, then I'm going to consider this a victory. So I'm glad you're watching that, because that is what it is. This is sequences and series. So we just want to know, does it add up to a finite number? And as Karan or somebody pointed out in the list, that they didn't just pay 4 cents or something. So that's it. We have a convergence series. So here we go. Now let's talk business again. So example 3. And going back to Jacipel, so where does this formula come from? If you take discrete math, then you get to prove this formula. So this formula comes from discrete math. I just knew it. So the idea is this one then. So here is your next series, and you're going to come this way. So this is, say, n equals 1 to infinity, n cubed. So write down this series for me. No, Karan, you don't have to memorize the formula, because we are not even going there. We're not interested in that kind of series. That is discrete math business. And if I will give you that formula. And this is an open notes test, Karan. Don't get cheeky again. So this is going to be what? Write out this series for me. I want you to type it in. So what it looks like. So number 1, write it out. So this will be, or just say it.
1 cubed, 2 cubed, 3 cubed,
There you
4
go,
cubed.
sir. 2 cubed, 3 cubed, 4 cubed. So what is your intuition about this one? That when you start adding up this to infinity, whether it will converge or diverge?
Well, I think it's going to diverge, because that's going
There
to
you
get
go, and
huge.
it is going to diverge, because this is your 4th term, so your nth term is going to be what? N cubed, right? So let's start this one then. The same thing. So number 2, I've got to find Sn. Oh, what is Sn? It is 1 cube plus 2 cube plus 3 cube all the way up to n cubed. The thing is, do I know what it adds up to? And discrete math will give you that formula. So I'm not going to spend too much time on that. Discrete math will give you that formula. I think Sn is n squared n plus 1 squared over 4. That's how I remember it. I think I'm okay, but you can Google the formula. And this is going to be the limit as n approaches infinity of Sn is going to be infinity, so the sequence diverges. But you know now how to play the game. But it's not easy to get the formula for all of them. So here is another series for you. Example 4. And this is me sort of making my point here. So tell me, what is this series now?
1
So
over
number
1, 1 over 2, 1 over 3.
Very good. Somewhere is your nth term, 1 over n, plus so on and so forth. So if you want to know the series converges or diverges, then you're going to find Sn. Well, Sn is 1 plus. My question is, if you want to find a formula for Sn, then you will have to add all those fractions. And so I'm just going to say to myself, not easy to do. And more importantly, I don't want to do it. That's too much algebra. I just want to know if the series converges or diverges. So I am going to take a rain check on this one, but I'm going to show to you later on with a very different idea, whether this series converges or diverges. So I'm just going to leave it there. And we are going to prove this next week. Why did I bring it up then? Moral of the story, not easy to find Sn. But having said that, there is one particular series, and I told you I like to move it like a story, but one particular series, there's one series, particular kind of series. You don't have to write this, just watch this, because I like to do the proof with you, and I'm going to do the proof with you, which is a geometric series. For which you can find Sn, and we are going to do that, no matter what geometric series. And then you can go on your merry way, go compute the limit, and tell me if a geometric series converges or diverges. So what is a geometric series? So a geometric series is made up by a geometric sequence. So what is a geometric sequence? Remember, we talked about this. There is a common ratio. And you have to identify A, which is the first term for me. So what does a geometric series look like? And here we go. So a geometric series. I'm going to write this, and you're going to tell me how this one goes. So this is, and I'm going to do the other way around this time. It's A plus AR plus AR squared plus AR cubed. You are going to give me the summation form of this. Before you do that, I'm just going to say this is the first term. This is the second term. This is the third term. This is the fourth term. And so let's check first things first. So I'm going to pause a little bit. If you're still writing, just let me know. And I want you to follow along. So in other words, I'm going to say completely stop writing, because I'm not going to ask you to ever prove this formula, but you're going to watch this with me, the proof. So ready? Nobody writing? Everybody just watching? Okay. So my first question is this a geometric series? I'm going to say yes, because when I take the next term over the previous, the next term over the previous, the next over the previous, the common ratio seems to be so type it in for me, please. So this over this, AR squared over AR. Very good. So the common ratio is R. The next question I want from you is, what is the nth term? Look at the pattern. The fourth term is AR cubed. The third term is AR squared. The second term is AR to the 1. Better than that, Sicilians? There we go, William. So it's going to be AR to the n minus 1. Because remember, 4 is matched with 3, 3 is matched with 2, meaning the exponent goes 1 down. So we are going to say this series is summation n equals 1 to infinity. AR to the n minus 1. Of course, A is not 0. Because if A is 0, it's all 0 anyways. So when I write this series that way, all I'm saying is when you put n equals 1, you will get this term, n equals 2, you will get this, n equals 3, you will get this term, and so on and so forth. So this is what that series is. What do we want to know? The same thing we wanted to know that, which is it converges or diverges. So to find if it converges or diverges, it seems I should take Sn, which is the sum of first n terms, which is going to be A plus AR plus AR squared. These terms, isn't it? Remember where we are getting. Always eyes on the prize. We are coming up with a formula for Sn. I want to know if I can solve for Sn. So here is some mathematical mumbo jumbo that I'm going to do, which means I'm going to say times this, multiply both sides by r. So if I do that, then I get r times Sn, which is ar plus ar squared plus ar cubed, and the last one gets multiplied by r, so it's going to be ar to the n. So far, so good. I don't want you to be writing, it's all there in the book. I just want you to be asking me questions. So far, so good. We're okay there. So I don't see any questions, so I'm going to go ahead and I'm going to say, this is equation number 2, this is equation number 1. I'm going to say I just want to go 1 minus 2. In other words, I want to subtract this from this. If I do that, then I claim that on this side, I get Sn minus r times Sn. What happens on the other side? Well, if you're going to subtract this from the above, then these get cancelled, and I am left with a minus ar to the n. So far, so good. Again, I don't see any questions there, and we are almost getting there. Remember, we wanted to find a formula for Sn. So I'm going to say 1 minus r times Sn is a minus ar to the n. So I'm going to say Sn is a 1 minus r to the n over 1 minus r. And now we can do something really, really spectacular, because to find if a geometric series converges or diverges, you were going to take the limit as n approaches infinity of this Sn. Well, I want to point out to you that a is a constant. Got nothing to do with n. The only part that has got to do with n is this one. And then what do I know? Oh, if r is less than 1, if 0 is less than r is less than 1, or I'm going to say -1 is less than r less than 1, then I know that this series converges. So I'm going to say if absolute value of r is less than 1. And what do I mean by that? And I'm just going to say if -1 is less than r is less than 1, what happens to this r to the n? It goes to 0. If r is greater than 1, or if r is less than -1, then we are talking about, well, this one just goes to infinity. And so we are ready to say that, and this is all there in the book, so a geometric series converges. So you're going to skip all of that. The geometric series converges if absolute value of r is less than 1, and it diverges if absolute value of r is greater than or equal to 1. So it converges and it diverges if absolute value of r is greater than or equal to 1. The question is, if you're saying it converges, what does it converge to? Oh, it converges to, I'm going to give you an example, so don't worry about that. Right now, just follow this. And it converges to a over 1 minus r. Okay? What the heck are we saying? So I'm just going to say, number 1, recognize it's a geometric series. How do I recognize that? Identify r and identify a. Remember, r is a common ratio. Number 2, look at the absolute value of r. If it is less than 1, you're going to say this series converges. That means you're saying this infinite sum adds up to a over 1 minus r. If absolute value of r is greater than or equal to 1, the series diverges, and we are not interested. It doesn't. So here is a quick example. And you are going to write this one for me. So, number 1, write out the terms. So what are the terms here?
1 over 2 to the 1, 1 over 2 to the 2, etc.
Very good. Infinitely many terms, yeah? There we go. So question is this a geometric series? And for that, the first term is easy to identify. I'm going to say, okay, the first term is half. Now I just want to check if this over this, this over this, this over this, the next over the previous, is it a constant? And is it a constant? And what is that constant? And that is your common ratio. So 1/4 over half, is that a constant? 1/8 over a quarter, is that a constant? And if it is constant, if it's the same number, can you tell me what that number is? Very good. So it is a geometric series. Why? Because this is the common ratio. So I'm going to go to number 2. So I'm going to say number 2, the common ratio half is less than 1. So I know the series converges. The question is, if it is converges, what does it add up to? And you're claiming it adds up to a over 1 minus r, which in this case is half over 1 minus half, which in this case is half over half, which is this, just adds up to 1. So you're saying if you do this infinite number of times, then it just adds up to 1. Are we okay now? And now I want to take a very, very different example. And again, I don't want anybody writing there. So where we have seen, so my claim is you have seen this infinite series. And I'm just going to say, let's talk about this number. Meaning it is 5.23 repeating. Now, Cecily, don't write this example. It is in the book anyways. It's going to be there anyway. So, ready for this one now. So I'm going to write this in some ways and see if you like it. So I'm saying, isn't this 5 plus 0.23 plus 0.0023 plus 0.000023? Would you agree?
Yes.
Okay, so I'm going to say, isn't this 5 plus 23 over 100 plus 23 over 100 square? Right? Plus 23 over 100 cubed. So I'm just looking at the addition of these terms because 5 is just 5. This part is that infinite series. So my question to you is this a geometric series? And if the answer is yes, I want everybody to give me the first term and the common ratio. So take your time, give me the first term and the common ratio. And so the first term would be, so Karan, share your thoughts, please. So I want the first term in the common ratio. Cecily, you're missing the point. 5 is outside, it's not part of the series because it doesn't fit this pattern. This is the series. 23 over 100, 23, yeah. Very good. So I'm going to go with Joshua. I'm going to write A is 23 over 100, which is 0.23, Joshua. Oh, you wrote it, sorry. And R is the one I don't agree. There we go. So Joshua is called, it is 1 over 100. Remember, where does R come from? This over this over this. So Joshua, the 23 cancels. Very good. So I'm going to look at the value of R. Oh, absolute value of R, 1 over 100. The question to you is this less than 1? Very good. So you know the series converges. Remember what you're saying, the infinite sum converges. Well, it converges to what? I'm going to say it converges to A over 1 minus R, which is what? Oh, it's 23 over 100. 1 minus 1 over 100. So I'm going to say it's 23 over 100 over 99 over 100. So this adds up to 23 over 99. What about that number? 5 plus 23 over 99. Now I'm killing myself here. So 99 times 5 is... Shouldn't have picked this example.
495.
And 495 plus 23. So stop, people, all your engineers, when you put this number in the calculator, what do you get? You get this one, which means what? The calculator doesn't know division. It's not going 518 divided by 99. No, it's not doing that. It's going to your series, which is this one, because this can be programmed. Because you write a program saying, okay, is R less than 1? It's a series. It converges. Where does it converge to? A over 1 minus R. If absolute value of R is greater than 1, then it does not. So here is an example where infinitely many terms add up to a finite number. So this series, this infinitely many terms add up to a finite number. But then here is what I want to end with. I want to end with a very last example, which kind of takes this. Oh, I've got 2 minutes. Perfect. So here we go. So here's the next one. So I seem to have understood that series is sum of terms of a sequence. And these are my comments now. What kind of sum? I'm going to say series is an infinite sum. So I'm going to make up the last example, which is this one. So what is this? This is a sequence. So if I write it out, it looks like it is 3 times 1 over 1 plus 5. That is n equals 1. N equals 2. It is 3 times 2 over 2 plus 5. N equals 3. It is 3 times 3 over 3 plus 5. Of course, you can compute these numbers, and you're going to say this is 3/6. This is 6 over 7. This is 9 over 8, and so on and so forth. The series, and I'm going to write the series down here. When I say this is the series, then we are talking about 3 over 6 plus 6 over 7 plus 9 over 8, and so on and so forth. So the question is, does this sequence converge? And the answer is so if I have to answer this question, I'm going to take limit as n approaches infinity of am. And what is am? This one. So this is going to be limit as n approaches infinity of 3n over n plus 5. And what is that limit?
Infinity.
Russell.
Yeah.
I'm going to take that answer from you because we did this last time. When n approaches infinity, and that is why I picked this problem. Right. How do we find the limit?
You substitute infinity in for n.
No, sir. Because infinity is ambiguous. So last semester we came up with a trick.
Oh.
And so I'm going to erase that, and I'm just going to have you recall that n approaches infinity was ambiguous. But what did we understand? That 1 over n approaches 0. So we said we would rewrite this as 3 over 1 plus 5 over n. What are we writing there? We are dividing by n throughout, each term by n. In other words, I claim that when you do this LCD and all of that, you will get this. So we are just rewriting, which is dividing by n throughout. I know, William, so will L'Hopital's work? Absolutely. But there is a direct way that you can do this. And so you're absolutely right, Amir. Limit as n approaches infinity. This is 3 because 5 over n goes to 0. And so this is a finite limit. So the sequence converges. I want you to understand what do we mean by that. You're saying if you follow this to eternity, this one looks like what? Half. And then 6 over 7, 9 over 8. Eventually, what do they start to look like? They all start to look like 3. They will all converge around that value of 3 as you go there. So remember, they start with half, but then you have this, and they are going to go up to 3. Are we okay now? So the sequence converges. What does it converge to? 3. What does that mean? Eventually, as n approaches infinity, all of these an's will start looking like 3. I just wanted to do something, but I think I'm going to stop. There is a homework that's due on Monday. Again, try to do as many problems as you can. These are my office hours now, so I don't want to go over because I know people have classes to go to. Or not, but these are the office hours.